There are stars that are literally the size of solar systems. So the more massive the star is, a star, let's say 10,000 times the mass of the sun, then it has to burn its fuel extremely quickly to stay up against the force of gravity. So they're very, very, very short-lived, the really massive stars in the universe. I don't know the figure for the biggest star, but one of the biggest you can see with the naked eye actually is Betelgeuse or Betelgeuse in Orion. And what's interesting about that is if you put it where the Earth is, then it would extend out pretty much to the orbit of Jupiter, I think even beyond the orbit of Jupiter. So if you imagine how far it is to Jupiter, that would be orbiting inside the star. And it's so big that we can see sunspots on the surface with telescopes here on Earth. So it's a vast star. That's a star at the end of its life that's swollen up. That isn't, however, the biggest. We can look so far out into space that we can see the light from just after the Big Bang, about 380,000 years after the Big Bang, actually. And in that light, before there were stars and galaxies, there are also patterns that match on to the way the galaxies are distributed in the sky today. And where did those patterns come from? Well, the best theory we have is a theory called inflation, which says that before Big Bang, in the sense that before the universe was very hot and very dense, it was still there and it was kind of cold and empty, but expanding very fast. And then that very fast stretch of the universe came to an end, slowed down, and in the slowing down, the universe got heated up and all the particles out of which the stars and galaxies are made were created. So that's called inflation. There's good evidence for that. Mars is the only planet we'll colonize beyond Earth, but it's an easy planet to colonize. It's got water in abundance below the surface, we're sure, or frozen in the ice caps. It's got all the minerals that we need to build a civilization. We have the technology to go and extract the water and turn the water into oxygen and hydrogen for us to breathe and to make rocket fuel and electricity, all the things we need to build a civilization. So we know how to do it. So it's just whether we want to or when we want to. Most of the plans I've seen to go to Mars involve setting up the base first with robots and then going to the base. So it's almost we build the base first and then we go and move in. And I think that's what we're going to do.
Do you think we need to terraform?
Terraforming is changing the atmosphere of the planet. And that's a longer term goal, but we know that we could do it in principle. There's a place called Hellas Basin on Mars, which is a big, almost certainly an impact basin actually. It's 9 kilometers down to the floor. So that means that although it's so big you couldn't see it, if you put Everest in the middle, you could look down on the summit from the edge. It's so deep that the atmospheric pressure is so high at the floor of the crater that liquid water can occasionally exist at the floor. So already, although Mars's atmosphere is very thin, there are places that are so low in altitude that the pressure is high enough for liquid to exist momentarily there, even now. So you can see that the atmosphere of Mars doesn't need a lot. It needs things like greenhouse effects, carbon dioxide and things thrown into the atmosphere. But then you can imagine growing plants, and the plants would produce oxygen, and the water's there for them to do that. And so you could imagine at some point in the future that we end up with an atmosphere on Mars again, because it did have one once.
Do you think that one day we will use wormholes to time travel?
It's one of the big questions in theoretical physics, whether those things, first of all, can exist. They can, given Einstein's theory, but there's a question about whether they would be stable. So there's a question about whether, if you tried to send information through them, then they would collapse. And it's a big debate at the moment, actually. You use it as a time machine to go into the past. And I think most physicists think not. They think that whilst they could exist, they would be unstable and collapse again. And so you'd never be able to send information through, let alone a person. Even one little light signal wouldn't get through it into the past. But we need the more advanced theory, the quantum theory of gravity, to be sure.
How the moon was made?
It was made in an impact. So very early on in the life of the solar system, so let's say 4.5 billion years ago or so, we think that a planet about the size of Mars collided with the young Earth. It's sort of a glancing blow, actually, which caused a lot of rubble to go out into space, formed momentarily a ring around the Earth, somewhat like the rings around Saturn, but then that ring very quickly coalesced into the moon. So we think that the moon is made of mainly bits of the Earth and also bits of this other planet that glanced off it. Something like 4.5 billion years ago. It's very, very early, very soon after the Earth formed.
As Jupiter is made of gas, could you fly a rocket straight through?
No. So you could fly a rocket through the upper bits of its atmosphere, where it's not quite as dense. But if you go down towards the core of Jupiter, the pressure becomes so high and the temperatures become very high. We think there are all sorts of exotic materials. We don't really know what's at the centre of Jupiter. We have a spacecraft called Juno at the moment, which is orbiting around Jupiter to answer that very question, trying to work out what is actually in the middle. We think that exotic things called metallic liquid hydrogen and all sorts of really strange materials. But if you tried to fly a rocket through the centre, it wouldn't get very far. It'd get squashed and crushed and melted. And then it may well hit something very solid indeed in the core.
And is there actually any proof for the multiverse theory?
So first of all, there's no proof. And secondly, there are lots of different versions. One of the ones that's interesting to physicists is something called the inflationary multiverse. So what is that? Well, the idea is our best theory of, let's say, the way that the galaxies are distributed in the sky. So we can map that. So it's something we can observe. We can look at where the galaxies are. Then we have a big map. It's called the Sloan Digital Sky Survey of where the galaxies are. And when you look at them, then they're random in a sense, but there's also some pattern to it. And in particular, they tend to, roughly speaking, lie on circles in the sky. So they're not completely randomly distributed. We can trace that all the way back to patterns that we see in the oldest light in the universe, which is the light that, if we look as far as we can out into space, then we're looking back in time. You might be ready to participate in the record event, to go at the Stargazing World Record, to go and look out at the night sky and get the most people ever looking out into the night sky at the same time. You could also likely, I think, see the Andromeda Galaxy. Not quite sure about the time when it's going to be up, but look at the Andromeda Galaxy. You're seeing light coming from it, which has travelled for 2 million years. So you're looking back in time, 2 million years, because you're seeing the Andromeda Galaxy as it was 2 million years ago. Now, many physicists think that inflation doesn't all stop at once, but stops in little patches. And so you have a little patch of this rapidly expanding universe that slows down and makes a big bang, and that would be our universe. And then the rest of it carries on, another little patch slows down and stops, and you get another big bang, and that would be a different universe. Another bit stops, and you get a big bang and a different universe, and so on. So that's called the inflationary multiverse, which is what was in your question, a multiverse. A load of bubble universes, if you like, essentially an infinite number. And that could be our reality. It really could be that our entire universe, which is much bigger than the universe we can see, with 2 trillion galaxies in it, is one bubble in a multiverse of bubble universes.
Why some planets like Earth and Jupiter have a magnetic field, and some planets like Mars and Venus don't.
So Mars is a small planet compared to the Earth. It means that its surface area is larger in relation to its volume. You see this in the natural world, actually, in animals. So things like little mice and bats have to work a lot harder to keep their body temperature. So all planets, when they form, you've got loads of rocks coalescing together. You get heat in the centre. That's added to by radioactive decay in the centre of the planets. So you've got a certain amount of heat in the core, and it's been radiated off into space. And the smaller the planet, the faster it radiates the heat through its surface, because its surface is bigger in relation to its volume. So you would expect a planet like Mars for its core to solidify. You've not got this nice iron core that can spin around anymore, molten iron core, and so you lose the magnetic field.
Since the universe contains billions of stars, why is the night sky dark?
The people thought about it for centuries, and it's called Olbers paradox. A Dutch astronomer, he was Dutch, wasn't he, Olbers?
I think so, yeah.
He thought about this, and he came to the conclusion that if the universe had been around forever and it was infinite in extent, then you could look up and every line of sight would end on a star. And if there'd been enough time, then the light would have traveled time to come to us, and because every line of sight would end on a star, you would see the sky ablaze with light, and it isn't. And that was enough for Olbers, I think, to say that the universe wasn't infinite in extent. So the answer is that we live in an expanding universe that's 13.8 billion years old, and that's ultimately why the sky isn't absolutely ablaze with light.
How can light be both a particle and a wave?
Experimentally, we find that when they interact in particle physics, what do we see? We see essentially a game of billiards, right? We see things with mass, or indeed with no mass, in the case of photons, little particles bouncing off each other. In order to describe where they're going to go. So you can ask the question, I've got a particle here, where's it going to be at some later time? Where's it going to go? Mathematics that describes where it's going to go is very wave-like. And so particles behave like waves in the sense that if you want to calculate where they're going to go, you end up with things you get with waves, properties of waves. So the way they move is not like the sort of particles we can imagine. If you bang these two together, you go boing, and that one goes off. You can calculate it, but the maths you use is quite wave-like. So for example, with a wave, you can get what's called interference, which means that the peak of one wave lines up with the trough of the other one, and the waves cancel out. And you get that with the way that particles move around. The best thing to say, my prejudice that particles are particles, but the way they move is not like the sort of particles we can imagine. You bang these two together, you go boing, and that one goes off, and you can calculate it all, but the maths you use is quite wavy and wave-like. So that's the way I look at it. Einstein's theory essentially predicts its own downfall. It says that, say at the centre of a black hole, let's say in a collapsing star, that there's no cutoff. It drives you in that sort of gravitational collapse to a point of infinite density, infinite space-time curvature. So it's a so-called singularity. But there are very good reasons to believe that that's not right. One of them is that we strongly expect black holes to be temporary structures. So they return their energy to the universe again, almost certainly, and this is through the process known as Hawking radiation, which is a first step, one of Stephen Hawking's great contributions. It's a first step towards bringing quantum mechanics and gravity together. And it has with an audience like this, it has the benefit of being quite easy to explain what's happening, actually. So I can do it if you want, which is that, so Hawking realized that quantum mechanics tells you that the empty space is never empty. So in particular, you can picture particles and antiparticles pop in and out of existence all the time. And so they pop into existence, they can borrow energy from the vacuum, if you like, for a certain amount of time before they return it to the vacuum again. And actually, the more energy they borrow, the less time they're allowed to borrow it for. That's called the energy-time uncertainty principle. So it's a fundamental part of quantum theory. So then you imagine on the so-called event horizon of a black hole, you get these particles pop in and out of existence. Just let me say, by the way, that these effects are measurable, and it's one of Feynman's contributions, one of the things he got his Nobel Prize for, showing how that in the light from hydrogen atoms, those little fluctuations have an effect, and you can take them into account. So we know they're there. So imagine on the event horizon of a black hole that the particles pop into existence, and they're going to come back together again. But one of them they end up on opposite sides of the event horizon. That means that they're what we call causally disconnected from each other. They can't come back. You've got one that's inside the black hole, if you like, can't get out. So what happens? Well, the particle that's outside is made real. It essentially radiates away, and it gets its energy from the black hole, ultimately. So the black hole radiates, it has a temperature, it shrinks because it's radiating energy away, and ultimately it returns its energy back to the universe again. So you sort of know that there's no end of time there. There's nothing really wrong in the centre of a black hole. It's just that the theory doesn't work, and it must be that quantum effects and these things, that something must stop you having these infinities and infinitely curved space, and that's the challenge. So we know there's a better theory. The theory predicts its own downfall. Same at the Big Bang, by the way. But we don't know what the theory is. We've not been clever enough to put it together. But the first steps are being made with things like Hawking radiation. Particle physics is a game of statistics, essentially. So it's like tossing a coin 100 times, and it is possible that you'll get 99 heads. Doesn't mean the coin is weighted. There's a possibility. And because we have up 600 million collisions per second on average at LHC, or more,
that means you've got huge numbers of collisions, huge amounts of data. So you're always getting things that look like new particles, and then they tend to go away again when you get more data. There's statistics fluctuating around. But we did have hints of which look very like new particles in the old data, and we need to take new data to see whether they go away or not. But one of them, it's a famous thing, it's called the diphoton excess, and it was about 750 times the mass of the proton. Now that's very heavy. The Higgs is 120 odd times the mass of the proton also. So a very heavy new particle it looked like, which was decaying into 2 particles of light. And so you can see that no one knew what this was, because there were over 200 theoretical papers published describing 200 different versions of what it might be. So nobody knows. Nobody knows even if it's there. It might go away. But if it stays, one of the suggestions is that it's this hint of extra spatial dimensions in the universe. So that there are ideas which go back to the 1930s called Kaluza-Klein gravitons, and the idea is that you can have extra spatial dimensions that are kind of curled up small, so we can't see them. And the analogy that's often given, which is a good one, is imagine a hose pipe at the bottom of your garden, and if you're a long way away from it, it looks like a line, sort of a one-dimensional thing. But if you walk up to it, you can see that it's actually curved up into a second dimension, so it's a two-dimensional thing, a cylinder. So space can be like that. And one of the signatures is that you get these signatures of heavy particles, kind of towers of them, almost like harmonics on a guitar string. And this looks like one of those, if it's there. So if we're very lucky, we see hints of something like extra dimensions, then you start being able to probe these effects. So gravity, potentially try to understand gravity by looking at collisions in particle accelerators, and then you're on your way. So if that it's very exciting if it turns out to be true. I just don't know. Many of these things go away when you get more statistics, but occasionally you're taken by surprise.
I'd like to know how you distinguish and identify the different kinds of things out in the cosmos that have an impact.
There are many independent measurements that build to our particular worldview at some time. So, for example, when you talk about the age of things, the age of the Earth, the accurate measurements come from, one thing is they come from radioactive dating, which is a very high precision technique to date rocks. And we can date the oldest rocks on the Earth, and we can date the oldest meteorites, and we can do those things. And we always get, for the oldest things, around 4 billion years or so, and you can hone it in from there. Then you can look at the sun, and you can say, well, we can do something called helioseismology, which is really like looking at solar earthquakes, if you like, solar quakes, and looking at the way the sun oscillates and rings. And you can use that to measure the amount of helium as a cross section through the sun. So we know that the sun shines by making hydrogen into helium in its core, which would suggest that there should be more helium in its core. And we know how bright the sun is, we know how much energy comes out, so we know the rate of nuclear reactions that we need to produce that amount of energy. So we can look and see how much helium's there, and that tells us how old the sun is. And you get the answer, which is about 4.7 billion years or so. So from a completely different measurement, you get a measurement that's consistent with the age of the Earth. So you build up this picture, in this sense, cosmology, from many different measurements, and they all appear consistent. So then you judge, if you make a measurement that jars with that whole lot, then it gives you a sense of that makes you perhaps suspicious. If it contradicts the whole swathe of other experiments, let's say we found out, well, actually I'll give you a very good example. Which is that in the 1990s, we had a measurement of the age of the universe, which at the time, based on the expansion rate we've measured, was about 11.5 billion years. And we had a measurement of the age of systems called globular clusters, which are old star clusters in the Milky Way galaxy. And the age of those was about 12 billion years. So the age of the universe was measured to be younger than the oldest objects in the universe. And that was the case in the 1990s. So what did people do? They just carried on measuring things. And then in 1998, a physicist who's now at ANU in Canberra in Australia, Brian Schmidt, and another team in America looking at supernova explosions in the distant universe and found out that they were dimmer than expected. And it turned out the interpretation was that the universe is accelerating in its expansion. A complete shock. It's like we thought the universe was slowing down. It turned it was speeding up. And that changed our measurement of the age to 13.8 billion years. But there was a time when there was a big inconsistency between the age of the universe and the oldest things in the universe, which were older than the universe. So you take data seriously and you hold it, and you're allowed to have a contradictory position. You don't need to make a judgment. You say, well, there's something wrong, but we'll carry on measuring. And what you find almost always, our worldview is quite sophisticated now, and the key thing is consistent.
Why must light have a finite speed? Why not infinite?
The very, very trivial answer is that that's the way the universe is constructed. But there's a possibly a slightly better answer. In Einstein's theory, the finite speed of light is built into the geometry. It defines the geometry of space and time. So you can sort of very briefly see that if you have a theory that says, based on experiment actually that led him to this, that says that space and time are essentially to be treated as dimensions. So you imagine this 4-dimensional sweep of space and time. Now obviously we have freedom of movement in space. We can go anywhere, backwards and forwards and up and down, come back to the same place. But in time we don't. We can't walk into the past. We can't halt our journey into the future, although we can vary the rate, actually, that we go into the future relative to other people. So there's something different about the time dimension to the space dimensions. And that difference in the geometry comes from a universal speed upon which everyone agrees. So it's a so-called invariant in the theory. And the last thing I'd say is that the speed of light is a red herring. If you know what that is, it's kind of it's a bad name for something, right? That light happens to go at the speed of light because photons are massless. And actually, in the theory, it is massless objects that have to go at that speed, and objects with mass that cannot exceed that speed. And the speed of massless objects is agreed upon by everybody, and that builds the geometry and stops you building time machines that allow you to go into the past, and leads to E equals mc squared, actually, because you have energy equals mass. So you can kind of see energy, mass, we can change mass into energy and vice versa. The sun does it all the time. What's the c squared got to do with it? Why is the speed of light squared the exchange rate between energy and mass? And actually you can kind of start to see when you realise that what that number is something to do with massless things, actually. So it's a coincidence, as far as we know, that light travels at the speed of light. It is possible that the universe is eternal. There's a lot of debate about it, actually, because Stephen Hawking and Hartle had a theorem that said that any universe that always expands has a beginning in time. But there are people that try that you can sort of get away. So that's cutting edge cosmology. I don't know what it would mean if it turned out that our measurements suggested that the universe is actually eternal, and it's only our bit of it that had a beginning in this Big Bang 13.8 billion years ago, but there was something before that, we think. How long that existed for, we don't know. Did the framework exist forever? Is it logically necessary? Does it need to be laid down? That's cutting edge. So I honestly don't know, is my answer. It's a question that we will perhaps answer very soon. So I think there's a suspicion now that there may be life on Mars, microbes. It looks like the conditions necessary to support life are present on the planet. In particular, liquid water below the surface, and some kind of geological activity. It looks very likely those conditions are also present on Saturn's moon Enceladus and Jupiter's moon Europa. So even on Pluto, actually, it looks like there's geological activity, a lot of water ice, which could be liquid below the surface. So the most likely missions are the European mission joint with Russia called ExoMars, which is part of it's already gone, an orbiting bit. There's a rover designed to go and look. And so there's within our lifetime, you can imagine a scenario where we find life has emerged spontaneously on another object in the solar system. Also, I should say, the other exciting thing is that we're at the level now where we can not only find planets around distant stars, we've found well over 2,000, but we can also analyse the atmospheres of the planets, and we're right on the edge of being able to do that. We've done it for some big gas giant planets. And we're looking, I think we've seen water vapour in one of the atmospheres, but it's a gas giant, so it'd be like Jupiter, so there won't be life there. But we're getting to the point now where we can start looking at the rocky planets. We're not quite there yet, and analysing the atmospheres, the chemical composition. And if, for example, you see a lot of oxygen, that's a smoking gun for photosynthesis. Oxygen atmospheres are unstable. I don't think there's any geology known that can replenish an oxygen atmosphere to 20% like ours. It's photosynthesis. So you can even imagine the most speculative of all. People say, what if you saw something like CFCs in an atmosphere, which is an industrial fingerprint? But we're there now. Within the next 20 years, we're going to be there where we can start looking into the atmospheres of these rocky planets. So it could be we discover life on a planet beyond the solar system from its chemical signature.